All right. So Mustafa just introduced the school. So I'm going to introduce Evan, and then we'll kick it off. So we're very pleased to have Evann Courdier joining us today from EPFL, that is the Swiss Federal Institute of Technology at Lausanne, Switzerland. So Evan works on fast image segmentation networks for drones, got a master's degree in general engineering, and another one in math and machine learning. Evan has done PyTorch tutorials before, such as the Applied Machine Learning Days workshop, which I think is EPFL also, right? A couple years in a row. He's been using PyTorch for a long time. Assistant instructor in deep learning, lectures at EPFL. So Evan is going to talk to us today about PyTorch. Last year at the school we did TensorFlow, so we thought it was appropriate. Everybody's really loving PyTorch nowadays. So with that, Evan, I'll hand it over to you. And we do have a Q&A feature on Zoom, so hopefully everything goes smoothly. But this is our first one, so if there are any sort of weird hiccups, we'll try to make it better for the next webinars. But please use the Q&A feature to submit questions. We're going to have a few places in Evan's presentation where you can stop, and we'll try to take a couple questions then before moving on. You can also post questions on Slack, but we may not be watching it during the presentation, during the webinar. So you can post questions on Slack, for example, if they don't get answered right now during the webinar. And Evan is on the Slack, and we'll try to be there throughout the week to answer questions and participate in discussions. So then Evan, I think you can get started.
Great. So welcome everybody to this fellow introduction to deep learning with PyTorch. So as Steve said, so I'm Evann Courdier, doing a PhD in deep learning for computer vision, and I'm working with PyTorch every day. So I try to walk you through the basics of PyTorch. So what to expect from this webinar? So at the end, you have an overview of the PyTorch ecosystem, and I get you to know all the basics tools for deep learning that PyTorch provides, and you'll be able to read and understand PyTorch code and hopefully quickly start coding. So the format of this webinar is 1 hour, 1 hour and 15 minutes. And since we only have 1 hour, I assume basic knowledge of Python and object-oriented programming, some gradient-based M machine learning, and maybe some experience with numerical computing language like MATLAB or NumPy, for example. I go back and forth with slides and notebooks so that I can give some explanation on the slides and then move on the notebooks for real-life examples. So let's dive in. So what's PyTorch? So that's a scientific computing library that is written for Python. So it's Python first, and it works very much like NumPy, but you get additionally GPU support, automatic differentiation and optimization algorithms that goes along, and all the necessary tools for deep learning that you might want to use. So it goes from all the loss functions, the optimizers, and so on. We'll have a look at that. So this is originally a port from the Torch library to Python, and in PyTorch you have a whole deep learning pipeline that exists. So here is the usual deep learning pipeline, and the one that PyTorch allows you to build. So you have, let me get some pointers. So you'll have some data set, have a training loop, get your model trained. You can put it to production using a production server. You can do your training distributed. What we'll focus on for this presentation is mostly how to get your data available for your model to be trained, and focus on how the training loop is built. What I want to do is basically to see how each bit of the training loop and try to find how to do this in PyTorch. So the usual skeleton of a program, deep learning program, will be first to create your model, load your data, and initialize all the hyperparameters that you might need. And then you have the training loop where you will get some samples, potentially move them on GPU if you have one, compute the model's prediction, the loss, and then compute the gradients of the loss with respect to the parameters of your model and update these parameters. So this is the training loop, and I want to focus on how you do each of these small bits in PyTorch. So that's how we'll build it bit by bit. And it actually all starts with samples, which are actually tensors in PyTorch. So let's see quickly what is tensor. So these are multi-dimensional arrays, very much like in NumPy, and similarly to NumPy, like the interface is similar for creation, indexing, masking. So here is an example of how the Torch interface is similar to the NumPy one. And let's jump in to see how it works in real life with creating tensors and so on. So here we go. I hope everybody can see properly the screen. If there is any delay or anything not working, please Steve, let me know. So first, for this first notebook, I will quickly go through because things are quite simple, and you may want to go back to it later if you want to find more information. We'll have offline notebooks. So this one I will quickly go through it. So to import the PyTorch library, you first need to import Torch, and then I create a tensor using the torch.tensor functions. As you can see, my tensor here has 2 dimensions. This is something you can check using the dim function on a tensor. And you also have shape and size functions to check the size of a given tensor. So here, my tensor has 2 times 3, a shape of 2 times 3. So you can perform a lot of operation with PyTorch, and there is 2 ways to call an operation. So either you can call, for example, torch.tensor, torch.operation on a tensor, or you can directly call the operation on the tensor itself. So with the example of the sum operation, I can simply call torch.sum or x.sum. This way of writing it is quite useful because you can then change the operators. So for example, if I want to compute the norm of the tensor x that I've built before, I can simply square the tensor, compute the sum, and then the square root. Chaining this operator is quite common in PyTorch, and of course you also have a .norm function that can allow you to do the same thing. One thing you want to pay attention to in PyTorch is whether your operation takes place in place or it is mutating the array. So for example, here I'll look at the add operation. So the add operation will add the value here to the tensor. So let's create a tensor that is an identity matrix. And if I apply this add operation to A, we see that I get a tensor that indeed has added 5 everywhere, but the tensor A hasn't been changed. Whereas there is an in-place version of this add operation that changed the tensor A in place. And here you can see that A has indeed been changed. So that's something you want to pay attention to, because in certain contexts in PyTorch, you might need to know when your tensor has been changed in place or has been mutated. So on a similar note, I want to show the difference between the assignment operator and the addition assignment operator. So here I have tensor A, and I add 1 to this tensor, and this operation here creates a new tensor. So therefore, if I run this cell, the A and A before tensors will be different tensors. However, if I use the addition assignment operator here, I will get the same tensor because A is modified in place through this operator. So that's something that you might encounter, and you might want to be aware that that in this case you get different tensors. Something that you use very often as well in deep learning is reshaping your tensors. In PyTorch, you do this using the view function. And so let's create a tensor that has 1 dimension and a size of 6. And so here I can choose to view my tensor. My tensor has a 2 times 3 tensor, and that's what the .view function allows you to do. And you can ask PyTorch makes it infer the missing dimension by putting -1, which is something you see also quite often in the code. So the view function is used very often, and there is also a reshape function like in NumPy in PyTorch. However, the reshape function will copy the data. It will not use the same data underlying, whereas the view function does use the same underlying data, which means there is no copy happening. Something else that you use very often is using a GPU. So in PyTorch, you might want to you might want to check first whether you have CUDA that is available on your machine, so a GPU available. So here I'm on my personal computer, so here I don't have CUDA available, but let's see on this machine I do have CUDA available, and so I first need to import Torch. All right, and then I should have CUDA available on this machine as well. So here it's true. Let's create a tensor and move it to GPU. So there is 2 ways in PyTorch to do so. One way is to call .CUDA on the tensor itself. So the first time you do so, it will take a little while, and then it will be immediate. And when you have your tensor on a GPU, you can check here that the device is written over there. You may want to bring it back to CPU, and there is a .cpu functions to do that. So I can do so and get my tensor to CPU. So this is the old way to do so, because there is a new, more convenient way that that exists. This first part is used in many older codes, so you might need to know it. However, the new way is more convenient because you can define a device at the beginning of your code, and then you don't need to worry about whether you're on CPU or on GPU. So in the beginning of your code, you can define device using the torch device function. Here you specify whether you want to be on CPU or on GPU, and which is the number of the GPU you want to use. And then you simply need to use the .to function to move your tensor X to the corresponding device. So for example, here I can move my tensor X to GPU using that directive. So that's quite useful, as I said, because you can put such a line at the beginning of your code that will check if CUDA is available, and if not, it will switch back to CPU. Otherwise, it will use the GPU, and then in your code, you don't need to worry about whether CUDA is available. You can just put your tensors to the proper device. All right, so let's switch back to the.
Hey, Evan, sorry to interrupt real quick. Just people are asking if they can see the notebooks now. Do you mind if we share your GitHub link?
Yeah, no, go ahead. You can share the links if you want.
Okay, thank you.
All right. So 2 last bits I want to cover about tensors are the type conversion and the conversion to NumPy. So to convert the type of a tensor, you can use the same 2 function as to move a tensor to different device. So here I've created the tensor Y, and you can see that by default this will be a float 32 tensor. And if you want, for example, to convert it to a float 16, you can do so with this kind of line. You can also convert it to an integer using this, again using this line as well. So this is something that you might need to convert between float, integers, Boolean, and so on. And one last thing that is interesting is to notice the interoperability between PyTorch and NumPy. You can very simply transform a NumPy array into a torch tensor. So here, for example, I create a NumPy array X, and then I convert it to a tensor array, a tensor torch tensor, sorry, using the from NumPy function, and then I can move Mike from torch to NumPy using the dot NumPy on a torch tensor. So here I have Y that is a torch tensor, and I can call the dot NumPy function to get a NumPy array. All right, so that's basically it for the basics on tensors. There is a lot of function that you will discover as you're using it. So what I propose is that we start building our training loop right now. So there will be like two main bits, which will be initializing different parameters, models, and so on, and then the training loop itself. So here we can already set the device. So we import Torch and we set the device that we want to use. And then in the training loop, we can already move our samples and labels to the proper device. And now let's see how we can get these samples and labels from a data set. So let me move back to the slides. And so very short recap on the tensors. So that's what you want to probably remember from what I've just shown. I'll let you go through it as well when we provide the slides. So this is what we've just done. So we have moved the sample and labels to GPU. We have seen how to do so. So this is the bits we have added. And now let's see how we actually can get these samples and labels from a real data set. So that's the crucial aspect of deep learning, to have data. So let's assume here we have training data. We have a data set. And here we have samples that we represent with the squares and different labels that are represented by the colors. So this could look like this, for example, on your file system. So here you could have two folders, one for the train split, the other one for the validation split. And in each of these folders, one folder per class. So here, for example, a human vs dog dataset. And now to make the link between your file system and your model that is waiting for input, PyTorch provides a dataset class. So here is representation of the dataset class. It's an object that you can query with an index, and that will return the corresponding sample from the dataset. So the only thing that a dataset has to implement is the two functions len and getItem. So len is a function that will return the number of items in the dataset, and getItem is a method that, given an index, will return the corresponding sample and its label. So, for example, in practice, you could have a data set with 5 samples. And then your data set, if you call the len function on it, it should return the number of samples in your data set. So here, 5. And then if you ask for the index 4 of the data set with indexing, then it should return the 4th index in your data, the fourth sample in your data set here, alongside with the label. So here, human. So as you see, it's always providing you with a tuple, so sample and label, and it does not necessarily hold the data. So you can see that it does not load all the images. It will just go fetch the one that you require. So then you have this data set. But when you work with data, you often need to process batches of samples to shuffle the data. And the dataset class doesn't provide this. For this, you will need to use a data loader. So data loader is another class that PyTorch provides, and that takes a dataset object as input, and that will help you with iterating over this dataset. So you can use it to create batches, to shuffle the data, to sample the data in a particular fashion. And you can also launch multiple workers to make the data loading faster. So here you can see when you use it in practice, you will be querying a mini batch to the data loader, which will be querying each index to the data set. And then it will return you mini batches of data that it might have shuffled if you have required it to do so. So with all that said, let's jump to the next Jupyter notebook about data, working with data. So I guess you can see properly my screen. So let's start here. So first, we will need to use to create a data set, and for that, PyTorch provides a dataset class that you can find in torch.utils.data. So Here we have we want to build a dummy dataset class, and so what I've done is that first I've created some data. So here I've created inside this data a tensor that has 10 random numbers, and then since it's a dataset, I need to implement two functions. The len functions, which here should return the length of the data, so I return the len of this tensor, and it should return and the getItem function that should return the sample corresponding to the index that you have in input. So here I get the data corresponding to the index, and then I create a label. Here I chose to have a label of 1 if my sample number is above 0.5 and 0 if it's less than 0.5. So here you can see the three functions that are needed for the dataset. And once you have done that, I haven't said, of course, but you inherit from dataset class here. Once you have done that, your dataset is ready to be used. So now to actually instantiate an object, you will just run that line. So here you instantiate an object and you have an instance of the dummy dataset, and then you can already check what the data attribute contains. So here you can see that it has created 10 random numbers, and we can check for example, the first one. So the first one should be here 0.88 indeed, and the label should be true. So here, as you can see, it returns indeed a tuple. You can check, for example, that if you query the fourth one here, you should get this number that has a label false. So our dataset is working properly. Now we have seen how a simple dataset works. We can already use it within a data loader. So to use the data loader, there is a class in PyTorch that is called data loader, and that you can also load from torch.utils.data. And then to create a data loader, that's very simple. You just need to provide the data set you want to iterate on, and then the batch size that you wish, and whether you want to shuffle it or not. So here I said that I want to shuffle and that I want batch size of 5. And then you can simply iterate through this data set using a simple for loop. So for sample label in loader, you can get your sample. So here I will show the first batch. So you can see there is indeed a batch of 5 samples alongside with 5 labels. So that's the basic of data sets and data loaders. However, the dataset we have used here is a very simple dataset with dummy data. So let's see how it would work with a real life example, if you wish, with the alien vs predator dataset. So this is a dataset that you can find on Kaggle, and that is a classification dataset between image of aliens and predators. So here on my on the repository, you can find such a dataset with a train and a validation folder, inside which you have the two classes alien and predator. And in each of these folder, you have multiple images that looks like this. So here is a predator, here is an alien. And now let's create a dataset class to load the data that is actually inside my folders here. So here I have created this alien predator dataset. So as you can see, the structure is the same as the dummy dataset before. So we have an init function loading the data, a len function returning the length, and a getItem function to give a sample when you provide an index. So here, in this case, you don't want to load all the image in memory. It might not be possible for a large dataset. Instead, what we will do is rather store the path to the images. So here I walk through the alien folder and I store all paths to alien images alongside with a label, the label 0. And then I do the same thing for the predator folder. So I walk through the predator folder, and for each image, I store the image path with the label 1. So here I chose label 0 and 1 for alien and predator. So just like this, I got all my path to my samples inside this array, self.image instances. And then what I need to implement are the len function and the getItem function. The len function simply will return the number of paths I have in my dataset this way. And then the getItem for a given index will return the image and the target. So first, from the index, I can retrieve the path and the target label that I have defined before. I can open the image. And then I simply need to return it alongside with the target. So here I get the path from the array. I open the image and I return the image alongside the target. Once this is done, so let's run this cell. I can create a data set providing the root and the split, so the train split here to use. And I can already check the length of my data set. So len data set we call the len function. So here I can see I have 694 samples, training samples. And let's run that and query the first sample. So here, as you can see, we get a tuple. So we get a pill image alongside the label 0. So here you get an image, and if we query the label 1, we can see we get another image. And so here we can notice two things. We can notice first that my image have different sizes. So here 225 times 225, and here 290 times 174. So we will need to have image of the same size to input to our model. And actually, we need tensors and not image as input to our model. So we need to transform this. And that's where we can use transformation from the Torch Vision package. So the Torch Vision package is actually a computer vision package that will help with a lot of tasks that you have to do in computer vision, that provides popular data sets and model architectures. So here in the Torch Vision package, you can load two transform to help with our problem, the two tensor, which helps to move an image, to convert an image to a tensor, and for example, the random crop, which allows to crop the image randomly to get a fixed size image. So let's see how to instantiate a simple transformation. You can instantiate a random crop given the size of the crop here, and the crop transform will be a function that you can apply on an image. So let's take the first image in our dataset. This is our alien. And then I can simply apply this crop transform here to our image. Here we go. We get a random crop of our image. And each time I will run this function, I will get different random crops. So now what we want is actually to crop our tensor and then crop our image and then convert it to a tensor. So we want to perform multiple transform. And to do that, to combine multiple transform, we can use the compose class from Torch Vision, which allows us here to compose different transformations. So here I do a random crop and then I move it to tensor. And then if I apply this all transform function to my image, I can see that indeed I get a tensor now. And if I check the shape of this tensor using the dot shape attribute, you can see that I get a tensor of size 100 by 100, so the crop I wanted to. And you can check that we have three channels for the RGB channels. So let's now apply this transform to our alien predator dataset. So if I come back here, what I can do is after loading the image, I can apply the all transform function. Here you go. And once that's done, you can check. So the date I load the data set again, but now when I query for the first sample, I get a tensor rather than an image and the class label corresponding. So with that being said, we have a data set that is ready to be used with our model. So a data set that provides tensor and that has a fixed size. So now we can see that with this new data set, we actually can use the very same code that I have above to create the data loader and to check the samples. So here, if I run the very same code, you can see that I get indeed a tensor of size with 4 dimensions. The first dimension is the batch size. So here you can see I have indeed a batch size of 5. And then you can see we have images. So 3 channels, 100 height and 100 width. And alongside with the sample, I plot the labels, and the labels here are 5 labels corresponding to the image. So what is interesting is that the data loader code doesn't change depending on the data set here. So we have built an alien predator dataset, but doing image classification is a pretty common task in deep learning, and therefore in Torch Vision there is also a dataset that automatically provides loading data from a specific folder structure. So here, if I provide the root of my dataset to the class image folder, then that is a class that exists in Torch Vision. Then it will automatically find the different classes, and basically it will do all the job that we have been doing in our dataset class that we have been defining here. Here. Great. So let's run this image folder. Here we provide the root and the transform that we want it to use, and we can see that we get indeed a proper sample from our dataset. So that's probably the main thing that you want to know for a dataset. So we have seen how to build a dataset and to use a data loader. And in case of image, you can use the transformation from Torch Vision, for example. So now we can incorporate these bits inside a training loop. So let's take as a task to classify this alien predator dataset. And so here I have added 3 lines to import transformation from Torch Vision, as well as the data loader and the image folder. And so here I have added some transformation. I load the dataset, and then I create a data loader. So I have added these 3 lines to prepare for iterating through the dataset later in the training loop. And then in the training loop, the only thing I have to add is to iterate through the dataset with a for loop. So 4 samples labeled in loader. That's the only line I have to add to my training loop. So here I can run that, even though this will not do anything for now. And yeah, that's it for the dataset and data loader. So let's move back to our slides to see where we are. So
Evan, do you have a moment for a couple of questions, or how are we doing on time?
Sure. So yeah, so here is where we are. So we have moved the model to move the samples to GPU, and we have loaded these samples from the dataset. And so before going forward, let's maybe answer a couple of questions.
Okay, great. I'll just read you a couple here. What does PyTorch do if you overflow GPU memory loading data to global memory? Do you need to do manual memory management? Which can be architecture dependent?
So usually PyTorch will just crash when there is an overflow in memory. So you will have data overflow error usually. This happens mostly on GPU. So you don't have to do specific data management most of the time. However, PyTorch provides some functions to clear them, like to release the memory on the GPUs if needed. I don't know if I have answered the whole question.
They can follow up on Slack if there's more. Maybe we can do, there's one more here that I think is pretty relevant right now. When we crop an image, does it not lose information? Is there a way to pad an image with white pixels to a greater size so that the features are not lost while cropping?
All right. So I've presented Torch Vision, and Torch Vision is a package that has a lot of functions to do image augmentation alongside with moving an image to tensor. You can also crop it. You can, as you have seen, but you can also do a lot of kind of cropping of rotation and so on. So of course you lose some information when you crop the image, but usually you will see that image multiple times with multiple crops. So usually that's I mean, that's not an issue. So you can, of course, Torch Vision provides a lot of functions to pad the image, to rescale it, and so on. But this is not necessarily a problem to crop the image while you are doing deep learning. When you crop the image, it allows actually to have a bigger batches because you have smaller images. So you can have bigger batches, which is usually good for convergence when you are training your model. Yeah. Anything else?
We can do more later, I think.
Yeah, if you want to add things to what I'm saying to questions, yeah, please feel free as well. Let's move on then. All right. So now that we have seen how to get batches of samples and labels from the dataset and move them to GPU, let's see how you can compute the model's prediction. So let's see first how you can actually create a model and compute its prediction. So PyTorch provides what we call a module that are reusable model components and that help you with building neural networks. So these are like building blocks to create all kinds of architectures. And these modules, this module class, will help to manage your model parameters. And PyTorch already provides a lot of built-in modules. So let's see how it helps to manage the parameters. So having a module, so a module class, actually helps to keep track of all the parameters in your model. So you may have a lot of convolutional layers, linear layers, patch normalization, and so on with parameters. And the module will actually be aware of its parameter. It will allow to quickly load and save the model. It will allow to reset all the gradients of the parameters because we'll be computing the gradients of these parameters and you might need at some point to reset them. We will see that later. And then you can move all your parameters to the GPU in one line as well. So you don't have to move all the parameters of each convolution to the GPU. You can just do it with the help of modules. So as I said, PyTorch provides a lot of predefined modules. So there is actually the torch.nn submodule of PyTorch, which is a whole library that is dedicated to neural network. And so they have convolutional layers, recurrent layers, activation functions, loss functions, and so on. So it's full of functions that will be that you might need. And then when you want to create your own modules, you can inherit from the torch.nn.module class, and then you can benefit from all the advantages that I have just talked about when I talked about managing parameters. So all the modules from the torch.nn library, like convolution, linear, and so on, they also inherit from this class. And when you want to inherit from torch.nn.module, you need to implement two functions. So you need to implement the init functions that will be like the usual init when you need that you need when you create a class. But in PyTorch specifically, this is where you will define all the subcomponents of your networks, and it will allow your module to become aware of the parameters because you define them in the init function. And then once you have defined what component your model should have, you define in the forward function how all these components will be connected together. So all the components that you have defined in the init. All right, so yeah, that's the basics on modules. Let's see how to use one and to create custom modules through some Jupyter Notebooks example. So first, we will need to import Torch as well, along with torch.nn that we usually import as nn. And then let's see as how you can instantiate a simple module that exists in the torch.nn library. So here I want to create a fully connected layer that is called linear in PyTorch. It's actually simply a matrix multiplication plus a bias. So to create this, I need to provide the number of features in and out. So here 5 features in and 2 features out of this fully connected layer. So that I call here linear regression model. And like this, I have created a linear layer, and therefore my model will have a weight and a bias parameter. So as you can see here, we can check that the weight of my models. So here I have indeed a weight that is of a size 2 times 5. And you can note that the type of the weight, so if I do type of the model weight, I get torch.nn.parameter. So a parameter is actually a wrapper on the tensor. And this wrapper of the tensor makes that the tensor is automatically added to the list of parameters of your model. When you use a parameter in the model will be aware that this tensor is a parameter because it has this parameter class. So for a module, you can get all the parameters. So here I'm using the named parameter function on the module, and I iterate through them. So it returns a tuple with names and tensors. So here I plot the name and the tensor shape. So you can see there is in the linear regression model a weight with size 2, 5, and a bias with size 2. And there is also a function that is just parameters that returns a generator for all the parameters inside the model. So here, if I use this function, I can get the 2 parameters weight and bias that is in my linear regression model. So then, how can we use this model? So a module in PyTorch, they will work on batches, which means that if you have a sample of feature size 5, for example, you will always need to have as first dimension the batch size, and then as second dimension your feature size. So here I'm creating like dummy data with random numbers, and actually here what I have is a tensor X with a batch size of 3, and then 5 dimension of 5 on the sample on the feature dimension. And then with this input, so an input of batch size 3, feature size 5, I can just call my model directly on the sample. So here, note that you don't call the forward explicitly. That's quite important. You don't want to do that, because if you do call the forward explicitly, you might not get some hooks that are defined in PyTorch might not get called. So what you want is really to call the module directly on the tensor X, your input X. And here we can get our output Y. So we can see that we get a batch size of 3 for the output, and then a feature size, if you wish, of the output of size 2, which is the output size of our linear model that we have defined. All right, so here we have seen a bit how to use a predefined module in PyTorch. So here our linear regression model, and then let's see how you can actually build your own module. So building your own module will be mostly using predefined module in PyTorch and connecting them through the forward function. So as I said before, you need to inherit from nn.module, and then here I will just initialize the different modules from the torch nn library that I want to use. So here I want to use 2 linear layers, so 2 fully connected layers in a row. So I just define them here, and then in the forward function, you can see that I am calling them recursively. So first I call the linear one, I apply a ReLU function, then I call the linear 2 and the output, and then I return this output. So just like this, my network, my minor network module is ready to be used. You can note that I have used here f.relu, and you might wonder where does this f come from. So here you can see it comes from torch.nn.functional. So as you can see, it's a kind of submodule of NN. So all the modules that you can find in NN, like linear and conversion and so on, you can also find them as functional inside the torch.nn.functional that we use sometimes. So here I use the ReLU function from this torch.nn.functional submodule. All right, so now our network is ready to be instantiated. So let's create one instance of our model. So here I just call the model with the parameters that I have specified here. So the input size of the first linear, the hidden size, and the number of classes in output of my second linear network. And PyTorch provides a handy way of displaying model. When you print it, you can see all the modules that are registered inside your network. So here I have, I can see that I have two linear layers. However, the order here does not necessarily match the order in which you will apply them in the forward. It's just about what parameters are inside your network. And then, just as before, when you want to call your model on the input, apply your model on the input X. Here, you note that you don't call the forward; you directly call the model on the input X. And here, I create an input X with a batch size 5 and with 10 input dimensions to match the input dimensions of my first linear layer. So when I run this, I get an output of size 5 times 2, so the batch size and the output of my linear layer. So what I have done here is actually building a sequential model that will run each different modules sequentially, and that's something you can do directly because this is something that is quite common. So there is a class that is called torch.nn.sequential, which will apply the module sequentially. So here we apply 3 modules sequentially: a linear modules, then a reusable module, then another linear modules, and this will actually match exactly what our custom module here is doing, with applying a linear, then a reusable, then another linear module. So this allows you to do much quicker, define a network that is actually sequential. And then you run it the same way as you would have run the previous one. So here we get also the output, batch size 5, output size 2. Right. Then a model can be moved to GPU, and you don't need to move each parameter separately to GPU. You can simply call .CUDA on your model to move directly all the parameters to GPU. So similarly to what I've said just before, .CUDA is the older way to do so, and the newer way to do so is to actually call the toDevice on your model. And assuming you have defined your device before, this will move your device to your model, to the proper device. As you can see, you don't assign you don't do model equal model.CUDA. You don't need to do this. This automatically moves all the parameters to the GPU. And probably the last bit we want to check on models is how to store and load them. After you have trained your models, you might want to be able to save them and load them later. So there is 2 ways to do so. And I will present both because there is one that is indeed easier, but it is not necessarily always safe. So let me show you. So the easy way is to just call torch.save, providing here your model and then the path. Doing so will just save my model, and then I can load it using the torch.load function. And here I can check I have indeed the same value, for example, for the 2 bytes. This function save will actually pickle the model. So it will use the pickle packages from Python to save the model. And actually, this will mean that what you will save will be bound to the folder structure that you have. So if your model is defined in a specific file, and then that you want to load your model and that the file has another name, for example, it won't be able to load it. So this might be a problem. And so there is a way to, let's say, rather than saving the whole model, just saving the value of the parameters. And that's what you can do with the state dict. So each module has a state dict that will return all the parameters of this model. So that's why it's actually useful to have the model aware of its parameter, because it's able to return all its parameter at once in the state dict, and then you can just save this state dict. So this state dict is really a dictionary mapping a name of the parameter with the value, so different weights. So if I save my model that way, I'm also allowed to then load it, but I need this time to use a function that is called load state dict. So I need to create my model first, which I didn't need to do before in the other way. I create my model first, and then I can use the load state dict function on my model to load the state dict that I have saved. And here you can check that indeed I have the same values for the model and the model that I just loaded. So the difference is really it's important to know a bit that with the first way, this is much simpler, but you need to make sure that your class names and organization of your folders won't change. Otherwise, using the state dict will just, rather than saving the model itself, simply save a Python dictionary with all the parameters of your model. One last thing we may want to cover now is how to compute a loss with PyTorch. So PyTorch comes already with a lot of predefined loss functions. So here we have L1, MSE loss, cross entropy, and so on. And let's run, and they're all existing inside the NN package, so the torch.nn. And so if we want to create, for example, an L1 loss function, we can just instantiate it this way, and then to apply it to compute the loss between two tensors, we can just pass it as argument to our loss function and get the loss. So here the L1 loss between the two tensors. So here, if we compute it manually, you can see that it is that it sums to 3, and then the loss function takes the mean of the inputs, so you get 1. So that's mostly it for PyTorch modules. Creating your own modules and using the one from PyTorch. So now what we can see is how we can add it to our training loop. So what we can do is simply to instantiate a model that way with a sequential, for example, and then to move it to the proper device. We also want to instantiate a loss function. So before I had the L1, here I want to use the cross entropy loss that PyTorch provides. That is more suited for classification problems. And then I can simply, in my training loop, add these two lines. The first line, apply my model on the samples. We get predictions. And then we compute the loss between the predictions and the correct labels. So that's what we do on this line, and we get the loss. So we have covered most of the steps. What is left is to see how to compute the gradients and to update the parameters with these gradients. So that's probably the most important step that we're going to see right now. Maybe let's cover the gradient computation, and then maybe have a small break for questions, if that's fine for you. So that's what we have done, computing the model prediction and computing the loss, which adds these two lines to the training loop. Now let's see a bit how you can compute gradients in PyTorch. So PyTorch has a package called AutoGrad, which will allow you to compute the gradients of your different parameters. So PyTorch is what we call a defined by run framework. And this means that the backpropagation is defined by how the code is run. So every single run of the code can be different. That's we will use, so this AutoGrad that is inside, that is the differentiation package of PyTorch. And so how does that work? Each tensor in PyTorch will have a recurse grad Boolean attribute. And then when you perform operation on the tensor, AutoGrad will create a computation graph to record all these operations. Then when you finish the computation, you can call the tensor backward to directly compute all the gradients automatically. So what you will have usually is that you will do a successive of computation that will lead to a loss. You will call loss.backward to compute the loss of, to compute the gradients of the loss with respect to each parameter. So before just jumping to the notebook, let's look at a quick example. One stuff I forgot is that the gradients are accumulated into the tensor.grad attribute. So note here that when you call the backward, the gradient that is computed will be added to the previous gradient that was inside the tensor.grad. It's not stored, it's accumulated, which means that if something is already there, you will add to the previous gradient. We will see a bit later why this happens that way. So as I said, just a quick example of how that could that works before jumping to the notebooks. So here we have the computation graph that could happen for the previous example. So we have an input X that we multiply by a weight matrix W. We add a bias B. We remove the value of the label Y. Then we square it, and we get a loss. So it's like kind of linear model. What you can note here is that X doesn't recur as grad, because we don't need to have the gradient of the loss with respect to X, because we don't want to update X. However, we want to update the weight. We want to update W and B, and therefore we will set their recurrence grad to true. Initially, their gradients are set to none, and then what we want is the gradient of the loss with respect to each parameters, and so we will call the backward function to get that. So we call loss.backward, and what we get is that the backward will automatically compute the derivative of the loss throughout all the chain of operation that we have applied, and then it will accumulate the gradient inside the grad attributes of this tensor. Only the tensors that, of course, recurs grad. Note again, I say accumulate, not store. If you run this, for example, if you run this same operation again, and that you call backward again on the loss, the gradient attribute of W will actually be twice as much, because it will accumulate and not be stored. Usually, this accumulation is useful to provide some more flexibility when you work with gradients of complex model. But here it won't be useful to us today, and that means that we will have to, after we have used the gradients to update our parameters, we will need to set them to 0. So that's something that you have to do in PyTorch, is to remember to set your gradients to 0 after you have used the gradients, so that for the next backward you will get fresh gradients. All right, let's jump into how you do that with AutoGrad. So, okay, great. So, how does AutoGrad works? Let's see that in practice. So, as I said, first you need to set the recurrence grad property on your tensor. So, when you create a tensor, by default, the recurrence grad will be to false, the recurrence grad Boolean attribute. And then, if you want to change this, you can use the recurrence grad function with an underscore at the end, trailing underscore, which allows you to change the value of the recurrence grad attribute. And here we can check that indeed we get a tensor X with recurrence grad equal to true. So once that's done, you can see how AutoGrad will actually track this operation. So let's do a simple addition operation, y equal x plus 2. And here you can see that our y functions also has the recurrence grad attribute equal to true, and that it has a gradient function. This gradient function is actually a pointer for AutoGrad to know which kind of operation it has to perform to compute the derivatives. So we won't dive into this, but it's interesting to see that through these gradient functions, AutoGrad is building a graph of the computation, and that's what will allow AutoGrad to compute the derivative later on. So if we continue and do some more computation on y, we can see that z will also recurse grad, and it will also have a gradient function that is different. So here it's the the backward function defined for the mean, for example. And so once we have seen that, we can check how this would look in the example that we had in the slides. So in the slides, we had this example of some linear prediction model. So we have an input X and a target Y that I define here, and then a tensor weight matrix W and a bias B. So you can see that here I will make W and B recurrence gradients so that we can update them with because these are the parameters that we want to update. So you can check here our two tensors, and then we can just run the line to compute the loss. And you can see that the loss is also a tensor that recurs gradient and that has a gradient function. So it knows what kind of operation has allowed to create the loss. And now if we check the gradient attribute of W and B, which is where the gradient is stored, you can see that at the beginning they have no gradient. So actually the gradient attributes are set to none. Then if we call backward on the loss tensor, it will compute the derivative with respect to B and W. And then if we check the gradients now, you can see that actually the gradient attribute of W and B has been populated with some data. However, X and Y that don't recur gradient have their gradient attributes set to none. Still, it hasn't changed. Let's just confirm what I've said about gradients that accumulate. So if I run this line again, I compute the loss again with the same values, and that I call backward again, we can check that the values of W and B, the gradients of W and B, are actually twice as much as they were before. So here you can see the gradients accumulate. So if you don't want this to happen, you will have to set the gradient to 0 between two backwards. So we have seen how to compute the loss for the gradients for our W and B here. How does it work for the model parameters if we have a model? So here we have a quick example of how this could work. So let's create a neural net. So here I create a simple sequential neural net where a linear, so a fully connected module is followed by a ReLU, then another fully connected module. And then I also create a loss function so that I can compute the loss and then backward. So here, if I ask for the first index of neural net, it will actually return the first module that is inside this sequential. So when running this cell, I actually get the first linear, which has indeed in feature 5 and out feature 10. And then I can check the weight of this module. We know that it's a linear module, it has a weight, so we can check this. And we can indeed see that it has 5 by 10, so 10 by 5 here size. And you can see again that it's a parameter and that recurrence grad is true. So this is something we might have not paid attention before in the previous notebook. And that's something that, that is also a characteristic of the parameter. So the parameter is registered by the model as being a parameter, and it has automatically the recurrence grad set to true. So you don't have to set the recurrence grad of all the parameters. It is by default. Then let's try to compute the loss of some predictions and some targets of and then to see how the gradients populate inside our neural net. So here I created some dummy data X and Y, dummy tensors. First, you see there is the batch size, which is here and here, and then the input size of X is 5. I can run my neural net calling it on X, get some predictions, and then compute the loss between the predictions and the value we want for Y here. And I get a given loss, which has a gradient function. So we have tracked the operation that have happened to get to that loss. And then we can check the gradient attribute of our neural of the weight function, sorry, of the weight parameter of our first linear. And you can see that the grad is still none because we haven't computed any gradient yet. But then when we will call backward on the loss, it will indeed compute the gradient for this weight. And if we check the value of the gradient of this weight tensor afterward, we can see that indeed it has been populated. Then, as I said, you need to zero the gradients before you actually do some other predictions and updates. So to do that, modules have a specific function that is called zero grad, and that you can call directly on the model. So here neural net, and this will zero the gradients of all the parameters. So if we run that, we can check that afterward the gradient of our weight tensor is set to 0. So that's something that you will need to do between each time you see a sample in your training loop, the zeroing the gradients. One last thing that is useful to know is how to stop this history tracking from autograd. All your parameters have by default their recurse grad to true, and during inference, when you don't want to update your parameters and you are simply wanting to get some predictions, you don't want autograd to create a computation graph, and you can do that with the no grad context. So if you write with torch.nograd, no computation graph will be built. So if I run that here, you can see that this operation y equal x to the power 2 creates a tensor y that recurs gradient. However, if you run the same operation inside the with torch.nograd context, the tensor that you create here doesn't recurse gradient, and you can see that the gradient and the grad function of z are both known. So that's the condensed basic of autograd. You might want to go through it again to make sure you have understood everything. For now, let's just see how we can add it to our training loop. So from what we had before, the only thing that we will actually add will not be inside the initialization part. It will be inside the training loop itself. So we add these 2 bits, the loss.backward function. So after having computed the loss, we will compute the gradients with respect to the loss for each parameter of the model, and that's with the loss.backward. Then we'll have to update the model parameters, and finally, we will need to set the gradient to 0, as I have said. Otherwise, they will accumulate over and over. Not that this 0 grad, I have put this line here, but you can put this line also at the beginning of the training loop. The only place where you don't want to put it is between the computation of the gradients and the update of the model with that gradients. So you don't want to put your 0 grad here. Otherwise, you will not update your model parameters because your gradients will always be 0. Otherwise, this 0 grad can nearly go anywhere. So that's it for our new training loop. Let's move back to the slides and see what we have added from our training loop. So we are nearly done. We have computed the gradients. And now we have this new step of zeroing the gradients that we have also implemented here and here. And what we need is simply to now update the model parameters, and so to optimize the model for reducing this loss.
Hey,
so,
Evan, sorry to interrupt.
If you can take a couple of questions.
Yeah, we could, but I'm just looking at the time. We got 15 minutes left, so I'm wondering if it makes sense to just try and finish and then see how many questions we can get to.
So,
what do you think?
So yeah, we can take the questions maybe afterward. I will try to run quickly through the 2 next notebook, which are not so long, and then we can take the question later.
Okay, yeah, just to make sure that we can finish the material and then decide how many questions we can take. I think that sounds good.
Yeah, I guess we can finish it. The optimizer part will be what we've seen now, and it will be relatively quick. So
okay,
let's
cool.
Let's do that then. So indeed, we will now see how to update the parameters using optimizers. So how to optimize parameters in PyTorch. So the torch module has a torch.optim submodule where we can find lots of different optimizers, an optimization algorithm. And the optimizer that you can construct will take as input a list of parameters that you want to optimize. And then when you want to actually do an optimization step, you can call the optimizer.step function to update the parameter. So all the parameters that are passed to the optimizer will be retained inside the optimizer object, and that way the optimizer can access the gradient attributes and update their values when you call optimizer.step. Finally, we know that we have to zero the gradients, and instead of using model.zeroGrad, you could also use optimizer.zeroGrad. This function does the same thing for the parameters that were passed to the optimizer. So maybe to make it a bit more concrete, let's have a quick drawing. So you have a model with and you can instantiate an optimizer, giving to this optimizer the parameter of this model. Then you will compute the output corresponding to the given input, which will give you a loss. We will call backward on that loss, which will compute the gradients of each parameters, and it will be stored inside the param attribute in the dot grad attribute of each parameters. And since the optimizer holds a kind of reference to the parameters of your model, it will also be able to access the dot grad attribute. And when you call the dot step, it will compute the update that it needs to do on the parameters, and it will apply it. So let's see how actually it works in practice. Let's jump to a Jupyter notebook. So here we go. First, we want to import the Optim package. So from Torch, I import Optim. And here, so this command allows me to check all the different optimizers that are provided by PyTorch. So you have Adagrad, Adadelta, HGD, Adam. So these are very common optimizers that are already implemented and then you can use out of the box. For an optimizer, as I said, you always need to provide parameters when you instantiate it. So here, I have chosen to use the SGD optimizer that is in the torch.optim submodule. And to create this optimizer, I need to provide the parameters. And here, I can use the parameter function that we have seen in the module notebook that allows us to directly get all the parameters of our model. So here, if I create the same neural net as before, this sequential neural net, running this line will create an optimizer that will have all the parameters of our neural net. And when we will call the step function, it will use the gradients that have been computed to update the parameters here. Depending on the optimizer you use, you might want to set other hyperparameters for optimization, so learning rate, rate decay, and so on. So let's see how you use it in practice. So I define a loss function here, and two dummy input and output. So X, which is an input with a batch size 15 and a feature size 10, and then a random output prediction. Sorry, a random label. I compute the prediction with my neural net, so I can just run neural net on X and get predictions. I compute the loss corresponding to this prediction between the prediction and the labels. And then I compute the gradients as we have seen just before. So after this line, we know that all the gradients of the parameters of the models has been computed. So here, let's check what is the value of the bias of my first linear layer in my neural net. So as you can see here, we have a bias with 5 terms, and now the optimizer.step will use the gradients of this bias, so the gradient of the loss with respect to this bias, to update these parameter values. So if we do the optimizer.step now, when we print the new bias, the new value for the bias, we can see that we have slightly different values because the optimizer has changed the value of this of the bias using the gradient attribute. So that's it. You just have to create the optimizer with the proper parameters that you want to optimize, and then after having computed the gradients, you simply need to call optimizer.step to request the optimizer for a gradient update. One thing you usually want to do also with optimizers, during your training, is to decay the learning rate. You might not want to keep the same learning rate all the time. And to do so, you have learning rate schedulers. And so in PyTorch, there is a couple of learning rate schedulers that already exist that allows to change the learning rate during the training. So there is a lot of kind of different schedulers here. I have shown like 4. And let's see how you would use the exponential learning rate scheduler, which each time you call it will multiply the current learning rate by some gamma value. So to instantiate a learning scheduler, you find the one you want in the optim.lr scheduler submodule, and then you need to pass the optimizer that you want to change the learning rate of. Here for this scheduler, I need to have a hyperparameter here that is by how much I want to multiply the learning rate each time. So here, remember, I instantiated my optimizer with a learning rate of 0.1. So here, what you can see is, I haven't instantiated that, sorry. So here what you can see is that I print the learning rate of my optimizer, which is 0.1. Then I do a step of scheduler, which is supposed to decay my learning rate by multiplying it by 0.8. And here I print the learning rate after the decay. And you can see that indeed the scheduler has decreased the learning rate from 0.1 to 0.08. So that's how you could use a scheduler inside your training. It's not used all the time, but they are available in PyTorch. Once you have seen that, we can just add this, add an optimizer to our training loop to finally finish and have a full training loop. So to the initialization part, what we need is to add this line, which instantiates a new optimizer. So here from the optim package, I choose the Std Optimizer. Then I pass to the model, pass to the optimizer the model parameters, which are the parameters I want to optimize on, and a given learning rate. And inside the training loop, I added this line, which will use the gradient that you have computed, that AutoGrad has computed with loss.backward. And then the optimizer will use these gradients to update the parameters. So you need to call the optimizer after having computed the gradient with backward. After having used this gradient, you can discard them by setting them to 0. As I've said, rather than using model.zeroGrad, you could also use optimizer.zeroGrad here, and it would do the exact same thing. So here we are good. So we have we can launch this, but once again, it will train you. So here this would train our model, but this would not display anything. So let's move back to the slides. And here we can see that we have fulfilled the loop. We have found finished, and we have added this line, which is how to optimize and update the parameters with the gradients computed with the line before. And now we have the full training loop that can be used to train any kind of model. So I think I have not much time left, but I will try to quickly go through a complete example of how to build and train a full model on a task, the MNIST task, the computer vision task MNIST. So let me go through this quickly inside the Jupyter notebooks, and you can probably ask more questions later on the Slack or after the webinar. So for this example, I have a couple of imports that you now know. And the network that we want to build is the LeNet. So here is a picture that is not very clear of the network we want to build. And so the details are here. So what we want to have is a couple of convolution ReLU max pooling layers. So I have convolution ReLU max pooling, another convolution ReLU max pooling, and then a convolution on a ReLU with given input and output channels. And then when I have decreased the size of the image using convolutional layers, I can use fully connected layers to do the final classification. So such a network, for such a network, you could build your custom module that way. So here I still inherit from an NN module, and then I choose to create two sequential, let's say two sequential model inside the init. So the first sequential would be the convolutional part, and the second sequential would be the fully connected part. So here you can see I use different modules from the NN package. So conv2d, relu, maxpool2d. So these are modules that you can find in the NN package and that you can find depending on what you need. So you can check them on the PyTorch doc. And then here I use linear layers to for my fully connected part. So once I have defined network I want, the modules I want to use, I simply need to tell which is the way I want to combine them. So first I apply on my input images the convolutional part. I get some output. Then this line, if you check, this will flatten the tensor, so it will actually take the image and output something that will have the size of the batch size and the remaining dimensions. So this is the flattening part, where you convert the tensors that is usually four-dimensional with the batch, the channel, the height and the width, to a tensor that will just have a batch size and a feature dimension. And then you apply the fully connected part on the output of this flattening. So you apply the convolutional net, you flatten the output, and then you apply the fully connected part to get the final predictions. So here with our init and our forward, this is enough to define this convolutional network. So we run this cell, and then we can instantiate a network if we wish so. So here I create a LeNet with this instantiation, and I use the print function from PyTorch to be able to check that that I have defined the proper network. So here you can see it prints all the operations that I want to perform. However, it's not necessarily the order in which I want to perform them. That's just what parameters and modules are inside my network. So let's check here all the parameters that are actually inside my model and that I want to optimize. You can see that I have a couple of bias and weights for the convolutional layers, and a couple of bias and weights as well for the fully connected layers. These are all the parameters that I want to optimize for my training. We can check if we want what would happen if we feed at the network with a random input. So we take an input that have a specific size, so batch size, channel, height, and width, and we feed it as input to our convolutional network. And we can see that in output, it will give us what we call log probabilities, because we have computed one of the last layer is a log softmax. So it gives us log probabilities. And the shape is 1 times 10. So 1 is the batch size, and 10 is the number of classes we want to classify in. Then we need to do two things. We need to define the data, like load the data, and then create our train functions. So loading the data now is something that we know how to do. So here we create two data sets. So we load the MNIST data set, and we load the two different splits. So here we load the train split, and here we load the test split of the MNIST data set. This is a data set that is already available in PyTorch, so you don't have to create your own class to deal with this data set. It even allows you to download this data set if you wish so. We define a couple of transformations. So we resize the image to 32 by 32, and we convert them to tensors. We provide this transformation to our data set, and then we create two loaders, one for the training set and another one for the testing set. So this is done simply as we have seen before by giving the data set here and the batch size we want to use alongside with the shuffle. We don't shuffle the test set, we shuffle the train set though. So when we have created this data set and data loader, the last thing we want to do is to create the train function that will actually train our network. So here I have chosen to actually write a train function and not just a training loop, so that I can call this function multiple times with different number of epochs. Here, so in this function, first I will want to create the optimizer I want to use. So in this case, I chose Adam, to which I give the parameters and the running rate. I define the criterion. Here it's a negative log likelihood loss, so that's adapted for classification. And then what we have seen together is this part of the loop. Sorry, this part of the loop. So we have seen how to go through each of the sample of the train loaders to move the data unlabeled to device, to compute the output of the model, to compute the loss between the output and the labels, to compute the gradients, to perform the optimization step by updating, that will update the parameters, and then to zero the gradients of your model. So that's what we have just seen. And here, what we do usually in deep learning is to perform this loop a certain amount of time. So what we call epoch is the number of time we will go through the whole data set. And so here we can choose to go through the data set a certain number of time until our network is trained enough. And something that you can see that I haven't explained before is that we need to set our model in train mode. The model has two modes, train and validation. And there is a very slight difference between the two. In train mode, when you are using batch normalization or dropout layers, the dropout layers will actually drop certain connections inside your network, which is something you don't want to see happening when you are using your network in inference. So when you don't want to have a dropout active in inference, you want to set your model in validation mode. However, when you train your network, you want your dropout to be active, and so you will set your model to train mode. It also has a similar action in the batch norm. So the batch norm will behave differently whether you are in validation or training mode. So make sure when you are training to use the training mode, and then when you are not training, you can use the validation mode. And I'll show just now how to switch to the validation mode. And so here we have the whole training loop. So for a certain number of epochs, we perform this loop. And then at the end of each epoch, we want to check the accuracy of our model. So we have written below an accuracy function that will compute the accuracy of our model on the given task. So the accuracy function, I won't go into detail, but one thing you can notice is that I use the model into eval mode. I put the model into eval mode, which usually allow to change the behavior of dropout and batch norm layers. And then I compute the number of correct samples over the number of total samples, which gives me the total accuracy of that accuracy that my model achieves during training and after training. So if I run these two cells, then I have a train function and an accuracy function that I can call. And here I will first define a device, the device I want to use. So in this case, on this laptop, I don't have a GPU, so I will use the CPU. And then I move my ConvNet to CPU, to the proper device, and I fill all that to my train function. And the train function will actually perform the training of my neural net. So here I have by default 3 epoch. So the training will run for 3 epochs, and with the output you can see that our model is actually training. So that's it for this notebook. Let's just wait for our final accuracy here, which is actually quite impressive. We can see that we can actually learn a task and NIST recognizing images with just a simple convolutional network and get already 96% of accuracy. So that's something that that is actually quite simple and easy to do in PyTorch with simply this kind of model that you can define in a couple of lines. I guess.
Yeah, Evan, we're about 6 minutes over, so if you could just wrap up in a quick
minute,
that'd
so
be
to
great.
wrap up, sorry, to wrap up, we have seen a couple of things on PyTorch, but there is much more you can discover. There is libraries, Torch for the Torch vision. You can see distributed pruning, quantization. There is a way to move to production and to have high performance scripts. So you can, there is a lot more things that you can discover with PyTorch. Maybe as a last word, if you're still wondering if you should use PyTorch, this is a nice quote from Andrei Karpathy. And basically, if you trust him, PyTorch makes your life better. I encourage you to check the GitHub that Steve has already provided in the chat, where we have the notebooks I have presented during this webinar, along with a detailed notebook for offline studies, so with lots of comments. And there's a couple of other resources that you want to check. All the great pictures I have taken from the deep learning book. This is an ebook that has been written by some PyTorch community members, and it's free until tomorrow, so I encourage you to get it, and some other good tutorials and courses that you might want to check out. I hope you enjoyed it, and yeah, that's it for me. Maybe Steve, if you want to take over.
Thank you very much, Evan. That was fantastic. Thanks for all the notebooks and the I mean, you say shallow dive, but really it was a deep dive in a lot of respects. We do have some questions still on Zoom. I don't know what your constraints are. If you're still able to stick around, you know, maybe we could go through one or two. Otherwise, we just take it to Slack. We're trying to keep track of the questions that we didn't answer.
I still have 30 minutes kind of, so I can go a bit over.
Okay, so I think, you know, some folks have been dropping off already, but let me just say apologies if we didn't get to anybody's questions. Please feel free to drop them on Slack and we'll get to them. But maybe we can just get to a couple right now if you're still interested in answering. So one of them, which I think is maybe worth touching on, and I don't know exactly what your level of familiarity is with other frameworks, but there were a couple people who asked about the relative comparisons, the strengths and weaknesses of different frameworks like Keras and TensorFlow versus PyTorch.
Yeah, so that's I guess that's a hard question to answer. That's a polemic question, I guess. I haven't really used much TensorFlow myself, so I wouldn't be very probably biased toward PyTorch. What I know is that for now the production part of TensorFlow is more mature. So if you want to put a model into production, there is it would be much easier using PyTorch using TensorFlow. Sorry. However, when you want to quickly like tweak a network and test a couple of things, you can easily debug. You can easily look into your gradients and do things like that in PyTorch that are usually much harder to do with TensorFlow. So I would say that PyTorch usually is more interesting in terms of for research kind of side when you want to try out things that are not like on the I mean that is not what everyone do. If you want to do what most people do and do it quickly, I guess Keras is probably your best friend, because with Keras you can really do something very quickly and very efficiently, I'd say. However, PyTorch will help you tweak a bit more these things and have more control. TensorFlow would be more production ready. That's mostly what I would say, and what most people would say, I guess.
Agreed. Let's see here. There was another question about can we define custom loss functions? This was a while ago. I didn't have a chance to bring it up, but maybe you just comment on whether it's possible and how you can implement custom loss functions.
Yeah, so a custom loss function would be basically just be a normal PyTorch I mean, a normal Python functions where you would use PyTorch provided functions. So you can definitely build your own loss function, but it would just be another Python function basically with using Torch provided functions, I guess.
Okay. Yeah, maybe in the interest of time, we could just let folks ask their remaining questions on Slack, I think. But you have notebook examples that folks can work through offline, right? Do you want to just
Sure, so that's what I've
mention what there is?
So yeah, I can show it. Show again where this is. So the link to our offline notebooks, online and offline notebooks are here. So you will find a live notebooks folder where you will find the notebooks I went through, but I didn't put any comments or any assignment. Whereas in the offline notebooks, which are notebooks that I previously made for another tutorial, you will find assignments, you will find much more comments, and they will be a bit longer. So I encourage you to go through these offline notebooks to get all the explanations. And for any questions, you can contact us through the Slack.
Yeah, and just say one more time, Evan will be on the Slack, and there will be a bunch of us also as well to try and field questions that folks have.